maybe we can you share your screen so we can check?
Can you allow me? I think from security settings. All right. So looks okay?
Yeah, perfect.
Cool.
Great. Okay, let's start. First, thank you everyone for joining our machine learning seminar today. We are very excited to have Vagelis Papalexakis here today to talk about tensor decomposition. Vagelis is an associate professor at the Computer Science and Engineering Department at University of California, Riverside. He received his PhD from the Computer Science Department at Carnegie Mellon University. Prior to CMU, he obtained his diploma and master's degree in electronic and computer engineering at the Technical University of Crete in Greece. He's broadly interested in spanning fields of, his interest spans fields of data science, machine learning, and he's broadly interested in tensor decomposition with lots of application in detection of misinformation on web and various real world problems, including explainable AI and so on. His work has appeared in top tier conferences and journals and has attracted a number of distinctions, including the 2017 SIGKDD Dissertation Award as a runner-up and several paper awards. He also received the NSF CAREER Award and the 2021 IEEE DSAA Next Generation Data Scientist Award. So with that, Vagelis, the floor is yours.
All right. Well, thank you so much for the very generous and kind introduction, and thank you so much for having me. So it's a great pleasure to kick off my year with a talk to you guys. I wish I was there in person, but you know, maybe one day soon. So again, thank you so much for being here. What I'm planning to do here is talk a little bit about recent work from our lab on tensor methods for multi-aspect graph mining, and I'll explain what those things mean. And I'm going to talk a little bit about sort of the more basic stuff, and then some recent works, and then how I see that moving forward into the future. So this is kind of like the outline. So I'm going to start a little bit with sort of some preliminaries and some introduction to tensors for graph mining, and then we're going to pick it up from there. All right. So imagine you have you know, a social network, and then you have a number of friends talking to each other. And in addition to the fact that they are connected in some way, you also observe the means under which they're communicating. So you see that Cartman is Skyping Stan, and maybe he's texting or snapping Kyle. And so the fact that you know which means of communication they're using can actually be additional data that can, number one, help us better, more precisely identify, you know, good communities in a graph like this, or do any kind of pre-presentation learning in a graph. And furthermore, it can help us understand and give more insight and intuition of what is this community about. So let's say a couple of people are using regular old school calling each other. Maybe those people are of a different demographic than, let's say, a community that is snapping or TikToking each other, right? And so this is kind of like, you know, this additional information is sort of those different views in which we observe the social interactions. And this is an example of a multi-aspect graph. Now, if we were to kind of start modeling it from an algebraic perspective, well, the first thing one could do is we can see like, oh, this could be like any graph can be presented as a matrix. And we can have an adjacency matrix that could be binary, could be weighted, could just represent any kind of way in which those people are connected. And doing that, we need to bring back a notion from our linear algebra, which has to do with a rank. And so even though this may you know, sound a little, you know, disconnected or scary, you know, the notion of a rank. So we have a in the chat. So There's a question saying the applications from different companies can share the data. Well, if they would, then that would be a scenario like the one I'm depicting. But sometimes you may have, there are data sets that record different ways of communication of different people. So for example, the MIT reality mining data set is a good example where they had a number of students and they were recording different ways in which they're interacting, right? But this is, Yunchao, that's a good point. If we had data from all those companies, we would probably be making a lot of money. So thank you for the question. So going back to the talk, we need to understand, given this matrix, what interesting things we can do with it. And in order to do anything interesting with a matrix, I claim the notion of a rank is very important. And a particular definition of the rank that I find very insightful, which is the following. So suppose you have two vectors, A and B here, and I promise you it's going to become less mathematical and less algebraic in a second, but a rank one matrix is basically an outer product of vector A and vector B. Why? Because basically we're just replicating that vector as many times as entries in B, multiplying by this particular number. Therefore, we have exactly one linearly independent column here, which is kind of the textbook definition we all remember from our classes. Now, why is this interesting? It's because the rank of a matrix is now defined as the minimum number of those things here, of those rank one matrices that can add up to the original data. And so by that definition, the rank of the matrix is measuring how much information, if you will, in the general sense of information, how many patterns are there in the data. And if we have a matrix that can be approximated by a low rank, that means that there is a small number of things that are there that we need to discover, right? And so that's something that we need to establish in order to be able to do anything from extracting data from a matrix. And that's exactly what a matrix factorization that I have here in the bottom would do, where let's say the first such rank one matrix would be, let's say, friends from work. The second one would be college friends. And the added benefit is that we can look at those columns of those vectors here and see, sort of some soft membership of nodes to basically different communities. And so this is all great, and there's been decades of great, hard, and insightful work on matrix factorization, right? But what's missing here is what about sort of this diversity of views that we were talking about, right? So surely we can somehow compact the graph into a single one and then treat it as a single sort of matrix, but any kind of aggregation may be actually ignoring important structure that differentiates a view from another view, right? And so how can one sort of do a similar kind of analysis while also embracing the multi-view sort of nature of the problem? Well, my personal favorite answer, and of course this is not the only answer that one can give, but the one that I have been focusing on is modeling this multi-view or multi-aspect graph as a tensor. For all intents and purposes, a tensor here is basically this multi-dimensional matrix. This here is a cube, is a three-mode tensor that has 3 dimensions, right? Each one of the frontal slices is an adjacency matrix, the one that I was showing in the previous slide. And the reason for my fascination over tensors is one of the major reasons is that tensor methods have been actually redeveloped and rediscovered in so many different fields and have been found to be useful in so many different applications across many different fields that to me signifies that there is an inherent sort of interestingness and utility to those raw tools that merits further understanding, both from a practical and a theoretical point of view. Just to give you a quick example, in chemometrics, where you have, let's say, different chemicals, let's say a blood sample or a beer or a wine that we wish to sort of understand what kind of chemicals you have in there, doing a similar kind of analysis that I'm proposing to discuss in the next few slides would basically give you, instead of communities, would give you in a tensor that is formulated by doing a spectral analysis of the chemical, it would give you the different chemicals in that mix. And in fact, those methods have actually been proven to be sort of industrial strength in sort of separating out different chemicals in the mix in a number of applications with chemometrics, including food quality, but as well as sort of cancer sort of biomarker detection and so on and so forth. And so that's kind of like a prime example where tensors have been really successful. And what I want to argue is that there actually can be a successful in problems like graph mining as well. And you know, this is kind of like where I'm going to start leading to. Now, if after the talk you feel that you really love tensors and you would like to read more, you can go in. We have a couple of different survey papers that can give you everything you would need. So one of them is a little more mathematical for all the algorithmic details you need to know. The other one is a little more geared towards more practical applications of the models, and you can pick and choose whichever one you'd like. But back to business now. What are we looking for? Similar to the matrix case, where we have the college friend and the work friends, here we're looking for those cubes in 3 dimensions, where now basically we have, again, a community of nodes connected to other nodes, but we also have that expressed as over a subset of the means of communication. So again, these blocks are giving us sort of a contextual community, which not only has which nodes are involved in it, but also under what communication sort of means. And fortuitously, the definition of the rank that I just told you a few slides before actually generalizes to as many dimensions as we may want to add. If we have a matrix, which is, you know, a 2-dimensional tensor, if you will, then we have outer product of 2 vectors, A and B. If we have a 3-mode tensor, then we have an outer product of 3 vectors. And as many modes we add, as many vectors we add. And so this definition generalizes to as many modes as we would like to have. We're going to stick to 3 modes here just because of the visual sort of ease of kind of showing things. But there are opportunities in cases where one can study 4 or 5 mode tensors, where, let's say, you're studying communication over time, over different means, and maybe what words were used in the communication. This is already like, you know, a bunch of modes to work with. But for ease of sort of exposition, we're going to stick to 3 modes from now on. And the way that we can sort of do this extraction of those rank 1 tensors, those triplets of vectors, the most popular way is the canonical or PARAFAC decomposition. It has a bunch of names also because it's been reinvented a bunch of times, independently one time from another. And again, this is basically trying to express the tensor as this low rank part, which is basically a sum of rank 1 tensors, and some noise that we're trying to minimize, right? And so we're not going to deal exactly on how we solve this. You know, there's a number of ways, many decades of work on how to derive different algorithms to solve this problem. And this is a non-convex optimization problem, so all we can hope for is a locally optimal solution, but there are good algorithms that we can use and build upon, right? But more importantly, you know, another thing is, how do we decide this R here? This is the rank, or rather the low rank, that we are trying to express our data in. And this is a really hard problem. So for all intents and purposes, we assume that it is given to us. In general, this is a hard problem. We have good heuristics. We have work both from my lab and from other colleagues and collaborators and everybody who's working on it that is advancing the state of the art in this. But this is a really hard problem that would merit its own entire talk. And so for now, let's assume that some invisible magical entity is giving this dimension to us. And given that, we are working with the tensor decomposition. And so why do we go with this tensor decomposition? Because one aspect of it is that it has a very intuitive interpretation. And so one way of looking at it is that each one of those rank 1 tensors, those triplets of vectors, is basically what we could call a co-cluster of, let's say, sender, receiver, and means of communication. And so this brings together all 3, in this case, entities in the tensor into a coherent pattern that is one of many, one of our patterns in that data, right? So one way of looking at it is this community viewpoint of things, where this co-cluster is basically this contextual community that I was referring to, if we have data that are of node to means of communication. The other way of looking at it, which is not entirely different, is that if we look across all those factors for a given node, let's say Eric Cartman here, this is basically, we can stack those vectors into a matrix. Those are going to be the rows of that matrix, right? those are going to be kind of embeddings basically of that node into that community space. And that community space is also a little more understandable. Each one of the dimensions means something. It means a distinct community in our data, right? So this is another way of looking at it, right? And doing this, actually dating back to 2013, we were the first to try this on a multi-view graph, not a social graph, but an academic graph. So the views were now, the nodes were authors, and we have different views, who cites whom, who co-authors papers with whom, and who uses similar terms with whom. And so those are different ways in which an academic can be connected to another academic, and the communities were research communities in DBLP. And we found that doing this kind of viewing the communities in this three-mode kind of outer product way of tensor decomposition actually outperformed any two-dimensional baseline at the time. And so this was, encouragement enough to proceed forward. Another thing I want to say by closing up the sort of the introductory stuff is that, well, a number of things can be on the third mode. Here, for example, we can have time, where each one of the slices is a different snapshot of the tensor in a different time, right? And so maybe, if we have a time evolving graph, we can then understand the birth and the demise of different communities. We can understand whether some, bursts in activity correlate to real life events or anomalies that may be present in our data. And there is a lot of work that not just uses vanilla tensor decomposition for that, but also tries to account for temporal smoothness or temporal burstiness and so on. And we have recent work in collaboration with Petko from Albany, Petko Bogdanov, on sort of manipulating time in certain ways to understand and identify interesting patterns this way. But this is basically what I'm going to say about this. And just switching now to a couple of examples on recent work that we use, build on top of this simple way of taking the tensor in this way, decomposing it into as many communities as we wish, and in an entirely unsupervised way, mind you, being able to identify that Cartman, let's say, belongs to community number 1, Kyle belongs to community number R, right? Because everything I've discussed so far does not use any community labels or any supervision, except for using a known number of communities that we assume is the rank, right? And so this is kind of like the basic thing we did back in 2013, and now a couple of things that extend in different ways that are sort of not covered by the basic sort of case, right? And the first thing is what happens if we, have some labels that are afforded to us, right? So if we had a small number of labels, right, where we knew for a fact that those 2 nodes are of community green, and those 3 nodes, I'm sorry, is there a question? Okay, maybe not. And those 3 nodes are, let's say, of community red, right? And there's a lot of great literature on, guilt by association, kind of label propagation, literature in graphs, where the general idea of, and then I'm trying to summarize an entire sort of subfield now, is that nodes that are close to each other in connectivity are more likely, if our graph obeys what we call homophily, are more likely to be of the same type, of the same community, of the same label, right? And so by propagating messages, each node propagating their community belief, we can actually kind of infer the community affiliations of every node in the graph, which is now in gray here, by sort of doing this exercise. And actually, this seems to work very well when we have graphs where homophily, meaning that nodes that are connected are likely to be of the same type, holds, right? And this is all great, and there's a lot of work on this particular area. But again, the problem is that in general, this kind of works when we have a single view, and maybe we have to jump across views, and there's, at least at the time of when we were thinking about this, there was not a perfect way of doing any of that. So one would have to do things on a view-by-view basis, right? And so motivated by the question of what if we have a little bit amount of supervision, what if we have a few labels, right? Can we do anything better? Staying in the same framework of tensor decomposition, but now doing a semi-supervised approach. And the idea is Yes, we can. And we are going to use a concept called coupling, which I'm going to briefly describe in the next few slides. So here, this is the original tensor, where it's a user by means of communication, exactly the same one I was showing you so far. And here on the side, what I've done is, for a small number of users, for a small number of nodes, I have exact community membership, right? So I know exactly which one of the K communities they belong to. And I have encoded that into sort of this one hot encoded variable that makes up the columns, if you will, the community label makes up the columns of that matrix, whose values are largely unknown, right? So I have information about a small number of nodes, and that's about it. Now, if I were to assume that I just have this whole matrix, just most of it is unknown, then there is a one-to-one correspondence between the rows of this matrix and the rows of this tensor. Also the columns, but it doesn't change much whichever way we couple it. And so if we assume that those two data sets are coupled, we can do one thing called coupled matrix tensor factorization, where the idea is we are decomposing, we are factorizing both data sets into the same community space. And so how would we express that? We would say that the tensor, again, is broken down into those triplets of vectors, those RAC1 tensors. The matrix is broken down into pairs of vectors, but the vectors that correspond to the first dimension, the rows, are exactly the same both for the tensor and the matrix. And so by forcing them to be the same variables, we are forcing the two data sets to be expressed in the same low rank space. And by doing that, we're actually using the information that this partial label matrix has to guide the structure, sort of the structure that is being extracted by the tensor. And in fact, this is exactly what we did. We added a couple of regularizations just to avoid noise and overfitting. But basically, the idea is we used a partially complete label matrix, coupled it with a tensor, and the decomposition then gives us community assignments that happen to be much more accurate than the entirely unsupervised case. And this is work with my recently former student, Ekta, who graduated very, very recently and is now at Walmart. Appeared at STM a few years ago. Let me just skip this and just go to the results. What I'm showing you here is for a number of data sets and a number of competing methods, the normalized mutual information between the actual community labeling and the labeling that is obtained by the algorithm. So higher is better, right? Maximum is 1. And we see here that for, the annotated bar is the one that is what I just described. And every other method is using either semi-supervision or multi-view information, but not both, right? And you see that in all cases, using both, combining both is actually giving us either the same as the best or better, right? And so that's very reassuring that we're actually combining semi-supervision and multi-view information in a meaningful manner. Furthermore, it's actually interesting that if we see how this works as we throttle the number of labels we are giving to the algorithm, this is the NMI as a function of a number of labels. And you see that for other methods that use partial label information, when we have a very few percentage of nodes labeled, they are not able to do as well as further down. Whereas because here we are also taking advantage of this structure, the multi-view structure in the data, we're actually able to do a little better and then consistently boost the performance as we increase the number of labels. And so this is also reassuring because this is telling us that somehow this method is using the labels in a meaningful way. And so that was also good. Are there any questions at this point? Feel free. I'm not sure what the protocol is. You can type them on the chat if you'd like, and I will try to keep an eye on it. Otherwise, I can also address them at the end. Moving on, now we're going to look at an extension. We're going to look at a limitation, first of all, of the vanilla tensor decomposition. What can it not give us, and how do we extend it to actually get what we want, right? Because as the title of this section says, sometimes we need to go beyond rank 1 if we need to express richer structure in the data. And let's look at an example, right? So far, we've been modeling every community as this rank one sort of tensor, this block, right? And so this is, in lack of a better sort of definition, is fine in expressing data in a certain way. But if we know that this is representing a community where A and B are, if you will, the space of the community, the sender and receiver kind of parts of the adjacency matrix, this can be very restrictive because rank one can only perfectly recover a full click, or not a click where everybody has the same weight, but a click where maybe we have different weights connecting every other node, but a click nevertheless. Why? Because if we recover the adjacency matrix that corresponds to this rank one tensor, all connections across involved nodes will have to be present when we reconstruct. And so if we want to represent a rich structure of a community, rank one won't do it, right? And there are many cases where, let's say we have not a full click, but maybe we have a star. Let's say we have a social media, an Instagram influencer that has a lot of followers following them, but they don't follow as many people. So that could manifest itself as a star node. And in fact, if we try to represent a star as a rank one matrix, we're going to have a really bad time, right? And so how do we now express richer stuff? That's the question that we wanted to answer. This is a paper again by Ekta from a few years ago. And this is inspired by earlier work by Danai Kutra from Michigan. She was at CMU at the time of that work, where the idea is try to express a graph as a vocabulary of smaller sort of structures that are user-defined, let's say stars, chains, cliques, bipartite cores, and so on, and use minimum description length to do so, right? And so inspired by this, what we want to do is we want to use a tensor formulation to extract those rich structures, and then we can use something like MDL to map them to known structures that are within a vocabulary that somebody gave to us. And so the thing is, we need to get rid of rank one, right? Because rank one, as I said, is going to see a click wherever, no matter whether there is a click there or not, right? And so how do we get rid of it? Well, maybe we don't really get rid of it, but we feed it a lot and we make it, a little fatter. So we take this A here and we actually expand it and we make it a rank L matrix with L vectors here in the dimension that we wish to capture richer structure, right? So for A and B, which are going to be modeling the adjacency matrix of that community, we are now given L vectors, rank L, which can be higher than one, ideally, in order to be able to express things like a star adjacency matrix that is not really expressible very well with a rank one matrix, right? So now, basically, instead of those triplets of vectors, we're going to be learning blocks, triplets, where now the first two vectors are matrices, rank L matrices, right? So that's kind of like the extension that we would like to do. And this, in fact, is a particular flavor of what's called a block term decomposition, which is a little more obscure tensor decomposition, that one version of it is basically breaking down the tensor into blocks like that. And so now you can see that one of those blocks can be representing a star, another one can be representing a near clique, and depending on how large or small we give L to be, we can actually give it to be large enough so that it can represent any complex kind of shape of community that we would like to encounter, right? And so this is that the general idea was to extract then those rich shapes using this block term decomposition. Each one of them now is encoded using MDL into any number of known shapes that we know. And then we just give them a name and we describe the multi-aspect graph by a collection of known shapes that were extracted by this block term decomposition. We tried out on different data sets, one of them being the airline sort of, data set where there are interesting patterns that are not adhering to the rank one model, where we differentiate between budget airlines and sort of more tier one airlines and how they do their business in terms of hubs versus not hubs, but regional versus big airports. And an interesting plot here that I just want to share is our ability to capture this rich structure as a function of this complexity parameter L of every block. And you can see that it's fairly insensitive, to the number we set. So after a while, if we set it high enough, it's going to be able to capture everything. And so and even smaller values for it are not going to miss useful structures. And this is an experiment where we deliberately planted known cliques and stars within a multi-aspect graph, and we were measuring how many of them we were able to recover successfully. All right, and I think if my timing is okay, then I may have like maybe, I don't know, 10 minutes. Is that right? Or should I shoot for 5?
No, 10 is absolutely fine.
Okay.
We can go till 1 p.m. our time, and then we will have 10-15 minutes for questions.
Okay, all right. Because I have only a small, like a few sort of discussion thoughts left, and the question here is, tensors are very near and dear to my heart, and they've been shown to work well. Part of their beauty is their simplicity and their ability to be able to be interpreted really nicely. But what is their place in a world where we have seen a lot of benefit in complicating things in a way that, and I'm not saying complicating things in a judgmental way, but going into more complex models that are very, very powerful and can help us do more, right? So where is the place of the methods that I'm describing in light of all those great sort of advances that have been made in deep learning and graphs in particular, but also beyond, right? So that's a question that is also very near and dear to my heart. And here are some thoughts and some recent results that hint towards directions that are maybe synergistic between, those kind of more traditional non-deep methods and deep methods, right? And so this is a sort of earlier work that we were trying to understand how can we express node embeddings of the style of deep walk or node to vec, which can be expressed as a matrix factorization, instead of a random walk and a skipgram sort of thing, similar to how word to vec can be expressed as a matrix factorization. So how can we tensorize that problem, especially in the cases where we have a graph and we have node features, right? So which is also the scenario where GCN is sort of thriving, right? We have a graph and we have features for every node of that graph, right? And what we thought about doing was, well, why don't we just take those feature vectors for each node, take a k-nearest neighbor graph of node by node on that feature space, and we make a new graph, right? So we just stack now the original graph and the feature graph, and we make a tensor. And maybe the original graph is a single graph or is a multi-view graph. But now if we took the features, we just stack them in this k-nearest neighbor graph fashion, and now we have a good old tensor, right? So that was the idea. And we wanted to see now how this performs compared to, if we do the decomposition, as I said, the rows of A and B, and we can check which one works better, are embeddings into that R-dimensional space. And comparing against, traditional sort of node embeddings that do not use feature information. And so this is kind of expected to do better, but also embeddings like TADW that uses feature information. And we see that this is a useful thing to do. So it works pretty well, and it kind of puts everything in the tensor framework, right? So this was sort of a kind of an earlier work that at the time, it didn't occur to us to kind of pit against GCNs, just because this is, again, unsupervised. And so we wanted to kind of compare against sort of, even though we're using features, unsupervised methods as well, right? Okay, we have a chat question. That is a good question. I am not certain about that, but I can, it may have to do with hyperparameter tuning, or just sometimes it may not just perform as well because it expects if my recollection is right, TDW expects textual features, and so maybe if you feed it something that is non-textual, it might not be doing as well. But that's something that my recollection is failing me right now. So, but that's a good observation. All right, thank you. So now moving forward, best paper at KDD 18, not by us, right, but by Stefan Gunenman's group and Zügner and collaborators, right, is this NETAC paper that is basically demonstrating how one can attack a graph convolutional network by perturbing, somehow perturbing connections between the nodes or perturbing the features or both, and in such a way that you, in a targeted way, you misclassify a particular node, right? And so that kind of work led us to try to understand, okay, are there any ways we can defend against this? And having had developed this T-Pine idea previously, we thought, well, those perturbations that we're making are minute in the grand scheme of things. And what is their effect in the singular value spectrum, if you will, of the graph, right? So we wanted to understand that and see whether something like T-Pine, which is the unsupervised kind of, tensorized version of what GCN would do, how does this work, right? So before we looked at that, we looked at what happens if we just take the graph, take a low rank approximation of it, forget about tensors, just an SVD approximation of it, and feed that to the GCN. And lo and behold, it actually works pretty well. So if you see here, this is before the attack, this is after the attack. This is the percentage of misclassified nodes. And this is for different ranks of approximating the perturbed graph. And you see that this is before, this is after, right? So, and you see that in many, many cases, we're able to restore up until the point. So if we have the rank of the approximation being really high, what ends up happening is that actually we're letting in some of the perturbations to the approximated graph, right? And so if we go sufficiently low rank, we're actually able to kind of almost eliminate the effect of the attack. And so this is just by using vanilla SVD. We also tried using, for GCNs, in order to protect the data, we use SVD. We feed the SVD approximation, and you see here that, after the attack, we're able to somehow bring things back. If we were doing T-Pine, which is sort of the tensor version, you can see that it doesn't work as well as a supervised deep sort of neural network for graphs, but it works pretty reasonably and also remains robust to most of the attacks, except for in political blog, it's kind of, drops, but not as drastically as a GCN, right? And so the lesson here was that, well, the notion of learning in this low dimensional space is low rank space, even if what you're going to do with it is, again, feed it to a neural network, is actually a useful one. And it can give you insight on how and why this particular attack worked and how you can stop it, right? So this was something that we're really happy when we saw. We presented at Wisdom a couple of years ago, and Negin is the lead author of the paper. She recently graduated last December, and we now have observed this particular phenomenon in a number of applications, including CNNs and image sort of classification, where, again, if we do any of those gradient-based attacks, the perturbations introduced are actually able to be cut away if we do a low-rank approximation. And there's a number of tensor models we can use there. I'm not going to go into the details of those, but we are able to basically batch a number of attacked images, approximate them in low-rank space, and feed them into the CNN. And now we're able to actually bring back the performance by and large to before attack levels. And so this is SLQ is a previous method by Polo Chow and collaborators, where they do a JPEG compression of patches of the image, which is kind of like in a similar spirit, is getting rid of high frequency noise, right? And this is kind of the performance of different tensorizations and approximations. And you see, this is, the higher the better, but sometimes it's a little slower than just JPEG compression, but we can actually go by batching and doing things more efficiently. We can actually do just as well almost per image with better quality than JPEG compression, which is again speaking to the, where is a good use of those tensor methods now that we are, are developing and we're reaping the benefits of all those really powerful and complex deep networks. And this is something that is ongoing work, not just for images, but understanding the extent of this particular phenomenon in different kinds of problems. And with that, I'd like to thank you all for your attention and the questions so far. I would like to thank my group of very photogenic PhD students and the sponsors for all our work, not just the work that I just discussed, that are listed down here. And I would welcome any questions you may have, and feel free to contact me if you think of any questions later after this Zoom meeting is over.
Fantastic. Let's thank our reviewer. And questions.
Hi, Professor. So thanks for the presentation. I have one question. So I'm not pretty sure about like the main idea. Is it like, so we want to like do the tensor decomposition to capture some low rank things which we think like these low rank things may embed some important information such as important graph structures, so that we feed them into the downstream like machine learning based model, we can gain more performance. Can I understand like this like third process?
So yeah, so thank you. This is a great point. So are you referring in general or at the last part? Just so that I mean, because there's a general answer to it, but also a specific one.
Like maybe both, like general
okay.
or the
yeah. So in general, there's multiple reasons why you want to do it. One of them, a primary one, the one you described, which is I want to learn a good unsupervised representation that compacts all the different views of the data into a single vector that hopefully now can do better in downstream tasks. The other side of the coin is that, well, maybe I'm interested in discovering stuff about the data. Now, this is a little more difficult to quantify because it has to do with understanding patterns in my data, but over and over again, tensor methods have been useful in that this representation is not only useful as a downstream task, but those dimensions mean something, and it's easy to tease that out, right? And so that it's a twofold kind of thing, but both the uses are equally valuable and equally sort of worth pursuing, if you will.
Yeah, thanks. So another question is about like, so yeah, if we first use it like the tensor decomposition to get some low rank things, like is it very like where it takes like a long time to get this representation and further feed them into the machine learning model or not? Maybe like as like the ranks goes up, like when we want to capture more complex topology like the stars, will it take more time compared to like just rank 1?
Yeah, so that's a great question. And of course, increasing the number of components or the complexity of the components will give you an increase in the complexity, right? But if I was giving this talk 20 years ago, I would say, yeah, actually, this is an issue and we need to make things faster. There is a lot of work by us and others that has made tensor decompositions actually pretty scalable and maybe not yet to the point of like, the scalability that one enjoys when they would like to train a convolution neural net, but I would say pretty comfortably, if you have a good enough machine, you can run millions or even more, tens of millions and upwards of that of nodes without having a problem, right? And so there are a lot of advances, but of course, once you increase the complexity, you may start hitting a wall, but that's something that happens with everything that we want to do.
Yeah, thanks. Yeah.
Thank you. Great questions. Thank you so much.
I have one question. In the last part of the talk, where all you need is low rank, right? So several questions actually. First, does the attacker know the defense mechanism? Does the attacker know that you are going to use this low rank approximation? Is the attacker oblivious or?
Yeah, that's a great question. So we actually try to enter. So if the attacker knows, we try to develop an attack that somehow tries to embed the components we would cut to lower rank components and somehow embed the attack in there. And in fact, if you do that, then the classification may fail, but what happens is that the attack is no longer kind of stealth, meaning that, what does stealth mean in a graph? Well, the degree distribution is not too messed up, right? But if you do that, then the degree distribution is messed up. Now, that is not to say that we've exhausted the opportunities that a knowledgeable attacker would exploit. This is something that is actually really of high interest to us in understanding how you can beat that in a clever way. But the strawman, if you will, way of hiding the things I would remove into low-rank components preemptively succeeds, but trivially so.
Got it. Thank you. Yeah, that helps a lot. And then the other question is, my background is more on images than graphs, but I think like they're completely analogous in this case, right? So one defense could be like, let's low pass filter our image,
exactly,
and then fit it in, and it's exactly like the similar idea, but then that's going to reduce the performance on clean data as well. So then the question is, what if we train a network on low pass filtered images or graphs in this case? And in the image domain, we know that that's going to lead to lower accuracy. Is that the same for in the graphs or not?
That's a great point. And just to amplify that point, this is like the work from Polo and friends on doing similar. I mean, they're doing a JPEG compression, which is a low pass filtering and doing a discrete cosine transformation of the thing. This is a fantastic question that I actually don't have an answer to. I mean, there may be one, but I just I'm not sure what would happen. Maybe Tyler has an idea, but I don't know. Really, that's a great point.
Thanks. Yeah, fantastic. Thank you.
Yeah, I'm also kind of not sure. But I had a question with, I don't remember if the method was called T-Pine, where you incorporated the KNN graph. I was wondering if you could maybe discuss again the intuitions of this KNN graph part.
Yeah, so basically the idea is we've seen that multi-view graph modeling as tensor is kind of like a good idea in giving us a nice representation, right? So how do we now, if we have features for a node, we cannot simply assume that to be a new view, right? We could do something to incorporate it to the whole decomposition. An alternative would be to couple the graph and the features, but because they are now referring to sort of fundamentally different distributions of data, right? So one of them can be features, could be bag of words. The other one is a graph. It's a little dicey what would happen if we were to just couple those things together, right? A tensor and just the features, although that's a very valid thing that one can do. And so what we wanted to do is, well, why don't we create a graph that captures the feature information, but in the same kind of graph space, just as a different view. And in fact, we also tried, let's say, I mean, because obviously K is a parameter, even like the kernel that you're using, right, of similarity is another parameter. You can basically now go wild and generate a number of different views, capturing, let's say, one nearest neighbor, two nearest neighbor, RBF kernel similarity versus, something Euclidean distance, whatever, right? And so then this is kind of a framework that just puts everything into the same structure and the same type of data, if you will, and then able to just reconcile them into a single representation, basically. That's the rationale behind it. Not that other forks in that line of thought are not worthy of exploring, that this is just the line of reasoning that we followed.
And here, could this type of method be applied when you don't actually have an underlying graph? So here, this Y matrix without that.
You can make it, exactly. You can make graphs out of those features, and then if you have different feature spaces, depends on whether there have been some cases where we tried doing that. The problem was that in those cases they were fully exploratory, so it's not that, like, it was psychological data where you have like people answering questions, and the answers to questionnaires were not necessarily very insightful of features so that you can kind of decompose them to a good space. But if you kind of make a graph out of those, you can get groups of people that are similar in some sense. But there's no, we didn't have any benchmark to test that against, right? It was giving meaningful results, but that was the end of it, right? And so, but this is a good point, that you can actually apply that to cases where there is no underlying graph and you just somehow making a lot of faulty, if you will, graphs and exploiting the multitude of them to get a better representation.
Okay. Thanks.
Yeah, but that's a good point. Yeah.
I just have one follow-up thing. So you're talking about this multi-view graphs, or like multi-view kind of graph structure. I know there are a couple of recent works like focusing on the information bottleneck. Like they want the views, like, so views kind of have different information about your input. So they want these views to be different from each other, but all of them keep some class information. So I'm wondering, could it be also incorporated here? Yeah.
So let me unpack, let me understand a little bit. So the information bottleneck, you can see it as a direct analog to the low rank approximation, albeit, the bottleneck could be a nonlinear, projection to that space, right? And so there's the kind of a parallel there. I'm not entirely sure exactly what happens in the different, across the different views, but what I can tell you and what happens here is that there is an inherent assumption that the different views are somehow correlated. Otherwise, you may as well treat them as separate matrices, right? And so I'm not familiar with a particular work that does this, but I would be happy to see it, and maybe I can help you figure out exactly where. It would be useful to me as well to figure out exactly what are the analogies there. But from what you're describing, it sounds like a thing where maybe this is perhaps doing the same thing I'm describing, but in a nonlinear projected way.
Yeah. I just saw them in some like traditional representation field, but yeah, haven't seen. But just like this work reminds me about that. But yeah, thank you.
Right, and rightfully so, because basically, whenever you see information bottleneck, then you may want to think about low rank approximation, but nonlinear perhaps, right?
Mm-hmm. Yeah.
Thank you. That's a good point. Good question. All right. Well, I'm not sure if there are any questions left, but if people want to ask something later, feel free to. If you Google my name, it's pretty unique, so you'll be able to find ways to find you can find me easily. So you can feel free to email me if you have any questions or ideas. I'll be happy to discuss further. And I really appreciate being your guest today, and hope to repeat that in person one day.
Absolutely. Thank you again for the fantastic talk. We really enjoyed it. And everyone, if you can unmute and thank the speaker one more time, and that would be great.
Thank you.
Thank you.
Thank you. It's in person. Yep.
Thank you all. Thank you all. Appreciate it. And yeah, hope you have a good weekend ahead and stay safe.
Thank you. You too.